Hi everyone. I hope you had a nice weekend and happy Monday. So we're gonna keep going with our topics because we are a little delayed with our schedule. And as we discussed before, we're gonna reduce the lecture time to hour and a half instead of 2 hours because I do want you to work on some activities and some practice. Um, this is a statistics and research methods class, so it's not just lecture based, but it's more like a project oriented class. So I do wanted to implement those part into our discussion. And that being said, we are going to have some projects coming up, so I will keep you posted on that. But uh, and before we start, I wanted to ask how you did with the homework assignment. Um, but since I can't get any answers from you at the moment, we will discuss this during our Q&A session. And I believe our first assignment was pretty straightforward because the topics we covered so far, um, those topics were supposed to be covered within 2 sessions, but we stretched it out to 4 sessions. So I believe it was enough time, and I apologize because if it was not as challenging as you thought it would be. So we will bring up the pace and we will keep moving forward. So that being said, I don't think I'm going to review the homework assignment because I think it will be a waste of time for many of you. I believe you pretty much successfully finished everything. And if you do have any questions, we will answer. I will answer those questions during our Q&A session, and I will post up the answers to the homework assignment. So don't worry about that, and we will. I'm not sure how it's gonna work out if I'm going to see your assignment. If I do see it, I will grade them and I will give you comments so you can go over those as well. But we are going to continue our discussion with data analysis. So to summarize what what we've been discussing so far, we've we've pretty much learned what statistics is and how it is used in our daily lives. And we briefly discussed the 5 number summary, and this is the most basic quote unquote report that we discussed. And we learned that uh, there are two main types of data, and that's categorical and quantitative, right? Qualitative and quantitative. So, and under quantitative, we learned that there is discrete and continuous. So that's where we pretty much left off so far. Oh yeah, and um, for your information, I have created notes from the textbook for you, so you can go over that as well. You will be given those notes through the staff there, I believe. So that's that. So what we've been discussing so far is called it's called um, descriptive statistics. Okay, and these are the basics of statistics. This is how we analyze data, and we're gonna be continuing with this. So let's just talk about how we describe this. All right. So first we talk about the center, and of course this is for what? This is for quantitative quantitative data because we don't know what the center is for qualitative, right? Um, center, spread, and shape. Okay, so these are the three things that we need to be aware of when we are analyzing any set of data. So we will be discussing this. So let's just jump on to these topics. Yeah. Oops. Oh, it's doing this again. Right. So I apologize for these messy notes. Okay, I'll try to make it as clean as possible. Alright, so let's discuss center. Center literally means where the, and I put this in a quotation mark, middle lies, right? So whenever we have a set of data, we need to know where the center lies, right? Where is the middle, right? And middle means two different things, so I just put this in quotation mark, right? Um, as we discussed before, we learned something about median, right? And this literally means the middle number, right? So the middle number, when you have a data set in an increasing order, say, and I'm making these up, so 7, 71, 73, 75, and 80, right? You just name out the middle number, which is this, right? So, and you come up with this number um, with this notation. So this is the convention, and when we speak about data and statistics, we lay out all the data, right? Observations, and we call each entry observations, right? We do that by x sub I. This is ith observation. So for example, we have these numbers, and let's just say that for for to make it easier, let's just say these are test scores, right? And the first test score, x sub 1 equals 70, x sub 2 equals 71, x sub 3 equals 75. Oh, sorry, should be 73. Um, yeah, should be 73, x of 4, 75, and x of 5, 80, right? The middle number here in this case is this one. And since we have 5 observations, it's always n plus 1 over 2 observation. And this is only if when the data are put in an increasing order, right? That makes sense. Because if you put them in, sorry, this, I don't know why it's gone, right? When the data, right? So you just, in this case, since we have 5 observations, right? So 5 plus 1, 6 over 2 is third. So 1, 2, 3. Third observation is the median, and which is the middle number. Alright, and this is a way of measuring the center. So where the middle number lies, that's the center, right? And now, we've briefly discussed this before. And now that is okay. So one way of describing the center was median, right? And the second way is average. And average, we are very, very, very familiar with it, right? We call this mean, mean and median. Average, average is notated. So let's just go over the notation first. By the sum of all observations, so x1 to x2, sum of all, so x sub n divided by n. So this is the average that we know, the regular one, right? And um, I'm pretty sure you guys are familiar with this, but let me just, okay, let me just um, write it down in terms of mathematical notation. Because statistics, since we deal with a lot of data, we like to make it short and concise because we don't want to write every single notation down for each, right? So we just use this with sigma. Okay, sigma, um, say xi, and I goes from 1 to n divided by n, right? Sigma is summation, right? This just means this x when I goes from 1 to n and divided by n. So this is the um, average of these data. And if you do the same for the test scores, right? If you add them up, so it's going to be 70 plus 71 plus 73 plus 75 plus 80 divided by n, the number of observation, which is 5. And if you do that, let me just quickly put this in my calculator. Is 73.5. Okay, so another important thing to notice, I mean, we do have two ways of measuring the center, median and mean. But when do we use which one? Like, we don't really know when to use mean or median. In this case, luckily, it was similar, right? 73 and 73.5 is pretty close. It's not that far off, but sometimes it will vary. And we're gonna discuss um, when that is the case, okay? So there is um, so say we have a data, and the data is okay. Why don't we just use the same data here, right? For example, this is mean versus median conversation. For example, we have 70, 71, 73, 75, and say we got 100 on the last test. Okay? So median in this case is always the same. Median is n plus 1 over 2th observation. And since these are in an increasing order, right? This is greater than 71, 71 is less than 71 is greater than 70, 73 is greater than 71. So this is increasing, right? Increasing. So we don't have to worry about the order. And same thing with median. As before, same as before, this is 5 plus 1 over 2, which is 3. So we're looking at the third observation. 1, 2, 3. This one. This is our median. Oh, I wrote that down. So median is 73. Same as before. But let's look at average, mean. If you add these numbers, 71, 73, 75 plus 100 divided by 5, we get 5 plus 100 divided by 5, we get 77. Ooh, where is it? Okay, equals 77.8. Okay, so this, comparing these two, it's very different from before, because before it was 73 and 73.5. In this case, it's 73 versus 77.8, and this is a pretty big difference. It's not that difference. It's not like we have 0 and 100 all of a sudden, but this is quite a change. And why is that? When comparing median and mean, these two values, right? We have to be aware that mean factors into account what we call, okay, let me go down a little, account what we call as outlier. Okay, outlier. Okay, and in this case, outlier is um what stands out of the rest of the data. Okay, so if you look at this data, 71, 70, 71, 73, 75, these are all similar, right? Similar ranges. So it's in all 70s, but in this case, 100 it's way up there. And it's not it's not normal to have these kind of observation, right? Since we only have 5 observations, it's pretty difficult to say that this is a significant observation. But in this case, this is obviously an outlier, right? Because 70s, these are all in 70s, but this is in 100. So mean always um, factors these outlier into account. Okay, and outlier is um, it's something that we need to be careful of. So whenever we're analyzing a data, right? If it's an outlier, we might want to take it out and discuss the rest of the values. Why? Because let's think about it. Like you got 70s all on the other exams, but you got 100 on the last exam. Why? Um, maybe you I don't know. Maybe the professor was nice enough to give you curves and extra points on these tests, and everyone else got 100 on the exam. So this is something that we need to be careful of. Um, so mean and median, um, these are something that you need to be careful of. And so let me just write that down. So mean, okay, mean is largely influenced. Oops. Sorry, I'm really bad with spelling. Okay, that's good. Influenced by outliers. Okay? And we're gonna talk about this later on, the shape of the distribution. And by distribution, I mean how the data how the data set is displayed. Let's put it that way. Distribution is just when you're graphing or displaying the data set, how does it how does it represent itself? Okay, so um, yeah, so we're gonna discuss this later on. But let me just say this. Okay. So when there is an outlier, what do you what is a better um what does okay, let me phrase this differently. So when there is an outlier, you might want to use median instead of mean, because it is mean is largely influenced by outliers, right? And for median, if there is an outlier, it doesn't matter if it's really big or small. It just measures the center, the middle number. So it doesn't really factor into account the outlier. So it might be a better measure of measuring the center. Okay, so that was mean and median. So that's how we measure the center, and that's the position of central value. Because it is important when we're looking at a data set, where is the center, right? And there are two, median and mean. Okay, so um, should we do an Excel? No, wait. Let's just move on. And I do want to go over some examples on Excel, but we will uh, do that when we go over variance and other topics as well. So we just discussed the center, right? And we want to discuss now. Where is my pen? Okay, the spread. Okay, so now we just discussed a center value, but we now want to discuss how it's spread out, right? Sometimes, okay, let me just draw a histogram. Okay, say something, um, you might have something like this as a histogram. Okay, and from this uh, graph, we know that this is the mean, and in this case, this will be the median as well. Okay, and we will discuss why that is the case later on. For spread, and let's say let's just give it a number. Say this is, I don't know, 50, and there is another histogram that looks like this. And say this is the mean, which is 50. And let's write it down. Okay. So, I mean, in statistics, it is important to say something about the center, and we did. And these are two different data sets, two very different. If you look at the spread, the graph here, it's very different, but they have the same center. So we need another way of differentiating these kind of distributions, right? So what we do in this case is okay. So we um, talk about the spread as well. Okay, and if you look at the first graph, it's more squished, right? It's more the data the data set is put together tightly, whereas this one is more spread out. So the value here might be 20, and the value here might be 40, right? So the range is bigger, obviously, in the second case, and the range here is smaller. And we we measure the spread by something called variation or variance. Okay? But before we do that, let me give you another definition. Okay? We called we measure spread by deviation. Okay? Deviation like in plain English means how far away are you from the norm. Okay, norm meaning here this is the mean, right? And mean is represented by x bar. Um, I think I should talk about this as well before we move on further with this topic. Um, so let me just go up a little, and I forgot to mention this above here. So mean, we have population mean. So population meaning the entire collection of units, and sample meaning sample is a subset of population. So a small portion of population is called the sample, and we call population mean, which is the true mean, right? It's a Greek letter called mu. We call this mu. And sample mean is what we collected, right? So it's not necessarily the true mean, but it might be. And we are hoping to get as close as to the population mean, and we call this x bar. Okay, so these are the notation, and we will later on do a hypothesis test, because what are we doing when we are collecting a sample? We want to have the sample mean as close as to the population mean, because what we're looking for is the population. What we're interested in is a population instead of sample, and that's why we're collecting a sample, a small portion of the population, so we can estimate, because it is impossible to have the population without doing any sampling. All right, so that's the notation that we use for population and sample mean. All right, so deviation. This is doing this again. I apologize. Okay, so I try to fix this. Let's see if it works. All right, so deviation. Um, Here, deviation means how far is the observation from the sample mean. Okay, so how far the observation is from the sample mean, right? And we notate it by the following. So deviation right equals equals sum of xi minus x bar. Okay, so xi meaning ith observation, correct? So if you use one of the examples up there, where am I? Okay, so let's use this data here. So see, this is the observation. We have 70, 71, 73, 75, and 100, and we got x bar of 77.8. The deviation is the following. So it's, again, using this notation, sum of all differences between x bar and the observation. So if you write it out, it's going to be 70 minus 77.8 plus, this is the first one, I equals 1. I equals 2 is 71 minus 77.8, right? So on and so forth. So the last one will be 100 minus 77.8. Okay? And we do this, and notice that we have negative numbers here, right? This is negative 7.8 here, plus and another negative, so negative 6.8. So okay, sorry about that. Negative 6.8 again, right? So on and so forth. And if we add these up, what do you think we're gonna get? What do you think? We are going to get 0. And that is the definition of the mean, because when we're looking for the mean, we're looking at the center of the observation. So whenever when we're adding all the observations together, we should get a 0, because that is the center of all your values, and that is the definition of x bar and the mean, right? So this does not really answer our question. Like, our question was how far is the observation from the center, and if you add these up, you get 0 for any case, and it doesn't make sense, right? This is why we use something called variation. Okay, and variation is the following. If I can find my okay, so variation, right? We're looking for this variation, and we measure this by something called variance. Instead of using deviation, we're going to square all the deviations. Okay, so what we're doing essentially is this: we are having xi, and then we subtract x bar, which is the mean, and then we're going to square them. And why do we square them? To get rid of all signs. So the problem here was that we had negative signs for some of them, and we had positive signs for some of them, and they cancel out at the end. And we don't want that to happen, so we're gonna square them. And by squaring them, we're gonna get rid of all the signs, plus or minus, and that's going to be very, very helpful for us. Okay. And I'm just going to give you the formula, and I'm gonna explain it, and why that works like that. Because I mean, to really prove this formula, we need something related to probability, which we didn't discuss yet. So I mean, if you're interested in the proof, we can always go over it. There's something called expected value and some expected values theorem that we have to use, but I would like to go over it if you want to go over it. So I'm just going to explain how this works. So let's look at this. So the formula for variance is s squared, and I will let you know why it's s squared. this is the formula. So sigma summation from I equals 1 to n. So for all observations for all data set, right? X sub I minus x bar squared, and then the whole thing over n minus 1. Okay, so this part we understand, right? This part is what we discussed before. This is a deviation squared to get rid of all the signs. And we're going to add all that from observation 1 to n. So for all observation, we're going to do that. And we have something here on the bottom, n minus 1. And you might ask, why n minus 1? Right? This is here because this is here to penalize small samples. So what I mean by this is the following. So when we're sampling the data, we want to have as many observations as possible. And you guys agree with that, right? Because the more data we have, the better off we are. And so, for example, we have where let's see what we can talk about. All right, so we're looking at the average income. We're looking at the income in the neighborhood, right? And say we pick out 5 people, and we're gonna ask them about their income. It's not really fair for the whole neighborhood. If you're just sampling 5 people, and 5 people, they might be the 5 richest people in that neighborhood, or the 5 poorest people in the neighborhood. So they don't really represent the population correctly. And that's why we want to penalize when we're having a small sample. We wanna we want it to show in the variance. So when we have a small sample, say something like 5, this is going to be a huge impact. Do you know what I mean? So first things first, variance, variance. We always want to. Let me just write it down this way. Ultimate goal when we are doing any statistical analysis, we want to minimize the variance. And I want you to kind of think about it. Why do we want to minimize the variance? If we're doing a statistical analysis, we want to find a pattern. We want to be able to predict what's happening, and we want to see what's going on within the data. And if we have a high variance, if we have a really big variance, that means that there is a lot of things going on, and there is a lot of variation. So variation, if we have a low variance, that means that we explain a lot of things going on, and we find a pattern. Right? So variance, it's always to have a small variance. That's always the best way to go, and that's our ultimate goal whenever we're doing something. We want to have lowest variance as possible. Okay, so lower the variance, and if you have a big number here, right? If you have a bigger number here, what are we going to have? We're going to have smaller value, right? So that's why whenever we have a bigger number for n, which represents the total number of our observations, that's better off for us. But if you have a small number, something like 3, that's going to make this a little less smaller and bigger, thus bigger. So this is the case for variance. So if you have a small sample, we're going to have a bigger variance. And if you look at the -1 part, say we have I don't know, let's just make it a nicer number. So say we have um, 3 observations, right? And on the top, say we have, I don't know, something like, this is a really, really big number, 60. And the observation here is 3. So here, if you divide it by 3 minus 1, it's going to be 2, and it's going to make it 30. And if we just use the number n, 60 over 3 is 20. So to understand why we have negative 1 part, it's going to make a big, big difference if the sample is small. But say if we have, I don't know, 60, we have, what should we do? Let's say we have 1,000 samples, and this is going to be what? 0.06. And making this, and reducing this by 199, it's not going to make it's not going to make a significant change. Do you know what I mean? Because this is what? This is going to be 0.606, blah, 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 blah. No. 0.0606, right? Let me just make sure. Yeah. So this is not going to make a much difference if the sample is large. So negative 1 part is there to penalize small sample, right? So in this case, it makes 10 of a bit difference, but this is only what? 0.00 something. So n minus 1 is there to penalize. And to talk about why we use SSC, the notation, that's the sample variance. You might wonder why we use variance. I mean, it is clear that we want to get rid of the sign, but again, this is squaring it. So we have a different unit if we square the number here, right? So say if we use, I don't know, if we use the data unit used here was centimeter, and if we square the number here, you're going to have centimeters squared, and that's not the correct unit that we use. So we take the root, the square root of S2, and we call that standard deviation. And we use these two pretty often, and I mean, standard deviation is sometimes more used often because it's in the same unit as what we're discussing in the topic, right? So this is, oh, I think I made that too big, but this is square root of variance. And we know how we have positive and negative square root. We just take the positive. So square root of variance, so it's going to be what? The whole sigma thing, xi minus x bar squared over n minus 1. And this is exactly the standard deviation. Alright? So these are the topics that we discussed. And now we want to go over something. So we discussed the spread, the center, and we want to go over the shape. But before we do that, let's just look at some examples of variance. Okay, so I drew some examples for us to go over this. Alright, so say that these 4 graphs here, histograms here, they have the same center, meaning they have the same x bar. Okay, and obviously graphs, they look very, very different. And this is why we are discussing this topic of variance, because even if they have the same center, same mean, that doesn't mean that they have the data look exactly the same as the other ones, right? So let me just number these graphs. 1, 2, 3, and 4. I'm gonna give you a minute or two to think about this, and I want you to think about the variance. Which one has the highest and lowest? So I want you to write down all the order in an increasing order of variance. Okay, which one has the highest, second highest, third highest, and the least variance? And again, remember that variance is how far are the data from the mean. Okay, so the further away they are, the higher the variance. Okay, just remember that, and I'll give you about 2 minutes, not even 2 minutes, like a minute or two to think about this, and I want you to label these graphs in an increasing order of variance. Okay? Okay, I believe that was enough time. So let's go over this. Which one do you think it has the highest variance? Okay, variance again, going over this. Variance, if it's high, more data spread out from the mean. Okay, so which graph represent this? Which of the following out of four? If there are more data further away from the mean, that means it has higher variance. And variance is low if it's packed around the center or the mean. Okay? So, um, let's look at number 2 first. Alright, so if you look at this data, you obviously see that more data here is more data further away from the mean, right? Here. And more and more further away. So the mean has the least frequency or relative frequency than other observations. Okay? So number 2 is the highest variance. Because why? Because you have more data further away from the mean. Correct? And which one has the second highest? This is the second highest. And we call this uniform distribution. But you don't have to know this because they are spread out evenly, right? And it's not really packed around the center, but it's not really further spread away from the mean as well. So this is going to be the second highest, but definitely this is less than this, the second case. Why? Because you have less data on these two tails, each end of the graph, but this one has higher, the more data spread out on these two ends, right? And the third highest, right, will be number 3, third highest. Highest. Why? Because, well, if you look at the graph here, you have the most data on the mean, right? And you have less and less data on each end of the center. So you have more data. It's like packed. You're squishing the data towards the mean, and that's why this is the third highest. And and it looks kind of like, we call this bell curve, and we're gonna learn this later on, and we call this normal distribution. All right, and the last but not least is number 4, and this is an exceptional case because this is when variance equals 0. There is no variance. You only have one number, all observation equals the same value at all time. So there is no variance. So if you just look at this formula, right? Square, and then you sum it up over and minus 1. Essentially here it's all 0 because x bar observation minus x bar, the mean is always, they're always the same. So this part is 0 and it has the lowest variance. Alright, so that's the discussion about variance, and now we're going to briefly talk about skewness. No, not skewness, sorry, I gave that away. The shape. Okay? So if you look at using these four examples, I used all these because these are something very exceptional again, and we call these symmetrical, right? So if you were to fold these graphs in half, right, about the mean, you will have the same, right? From this side to that side is the same. From this side to that side is the same. Same here. It's all symmetrical, and we call this symmetrical, right? In symmetrical case, I'm pretty sure you've noticed already. Mean equals median. Middle number is always the same as the mean average, and that's the case for all symmetrical data, right? And we have for all the other ones we call that asymmetrical, and which is, if it's not symmetrical, we call that asymmetrical. And also we have, okay, for asymmetrical cases, let's look at some examples. Right, say we have something like this. Okay, and if you were to kind of like draw it out in a line graph, it looks like this, right? And we see that we call these endpoints, we call these tails, right? And this one will be the left tail, and this will be the right tail, right? And we see that this has a longer right tail, right? And we call this skewed. This is skewed, right? It's not symmetrical, and this is skewed to the right because right side has longer tail. And similarly, if you have something like this, something like this is skewed to the left. And interestingly enough, the mean versus median conversation comes into play here. So what do you think the difference between the mean and median is for this case, skewed to the right? Okay, so let's look at this. Let's call median M, and mean is always x bar, right? So which one do you think is bigger? Right? In this case, x bar is bigger. Why? Because um, x bar always follows the tail. Because if you have more data, if you have the data on the right side, then it goes along with the tail. So, for example, if the median is somewhere here, the mean will be somewhere here. Because it follows the tail. It's not resistant. It's not resistant to outliers, or it's not resistant to any data further up. So it follows the tail here. And same thing here, if we were to compare these two, median and x bar will be smaller. X bar follows the tail, the longer side. So x bar, if it's here, median will be something like here. So this is like this. So, and discussing the outliers, say if we have a bell shape, like symmetrical, but if we have an outlier here somewhere, right? The graph would look like this. And although this is symmetrical here, because of that, it's going to be skewed to the right. And that's why average is going to be affected by the outlier, because it follows a tail. And it would be something like here, where the median is here, right? So that's the discussion of descriptive statistics, where we talk about shape, center, and variance. And now we're going to do an example in Excel, how to use all these informations and do it on Excel. So let's move on to Excel now. Okay, so here we are with Excel, and this is a class activity file on Excel. We're gonna do an example together, and I'm gonna let you practice on your own computer. So Excel it's the greatest invention of all time, as I said before, because it has everything built into it. But I do want to I want you to practice using the formula before we just conveniently use the standard deviation or the mean function. I just want you to be familiar with this. So we're gonna look for the variance, the mean, and everything. But let's just look at how we would use it for if we didn't have any functions built in. So I mean, average is pretty simple, right? We've been talking about it for a while. So average is, let me just make this a little bigger for you. Let's make it 200% so everyone can see. So actually, this is the data from the homework. So this is the earthquake magnitudes. And here we're going to find the average, or or why don't we just use the statistical term mean, right? So mean equals average, right? And then open parentheses, and you have to give it a range where the data starts and end. And we're gonna do that from A4 down to A48, and then we're gonna close parentheses and enter, right? And if we go up, we get the average value. Okay. You know what? I'm just gonna add a column here. Okay, so this is the magnitude, and these are the observations we have. Now we're gonna look for the variance. All right. If you remember, variance equals what? Observation minus mean, and then you square the value divided by n minus 1. And we're gonna use that formula to find the variance. Okay, so why don't we do this? these are here are the x values, the observations. So we're gonna do equals. We're gonna select these data, and then we're gonna subtract the mean. Okay? So that takes care of what? X sub I minus x bar part. So we're gonna do that for the rest of them, but if we drag the values down, we want to lock this value. We want to lock the mean because this stays the same. So we're gonna press F4 to lock the value and enter. And we're gonna drag this down all the way down to 48. And we're gonna get these values, right? Right, actually we might need another column, so let me add another column. And this takes care of, let me just label this. This is x sub I minus, let me just say x bar. Okay? So these are the x's. Let me just label these two, xi. Okay, these are xi observations, and we have xi minus x bar, and then we have to square these numbers, right? So what do? Equals. There is a function for exponent, but this is only square. You only multiply it by 2. This times is the star, the same value, right? And that takes care of the negative sign. And we're gonna drag this down all the way down to 40 something, 48, and we get these values. And again, if you look at the values, I mean the formulas here, you see that these are all correctly formed. Excel is very smart. So this is say xi minus x bar to the second power squared. So what do we do next? We what do we do? We divide these values, and we do what? We divide it by n minus 1. But we don't know what n equals. So why don't we just look for n? Right? So n is a number of observations. So what we're going to do is we're going to COUNTIF. It just doesn't do count because the value here is already a number. So it doesn't do any, there is no function counting. Okay, so we're gonna do COUNTIF. So we can do something like this. COUNTIF. There are a lot of ways to doing it. So if you have your own way, you can do that. But select the range first and say, oops, if it's greater than 0, then count. Right? That applies here. So n equals 45. So it counted all the values. Okay, so we calculated these values here, and now we have the sigma, right? So we are adding all these values for I sub 1 to I sub 45. So we're gonna do the sigma, right? Summing all of them, so it's going to be the sum, and give it a range. We're adding all these numbers, and enter. And it gives us the value of this much. And what do we do next? We divide this number, the sigma, by n minus 1. Right? So the variance, what we're looking for ultimately, is this is sigma divided by n minus 1. And this is the variance we get. Okay? So this is how you would calculate the variance manually. But there is a function built into it uh, in Excel. So we will use that function as well. So if you were looking, and let's just compare if it's correct. So if you so, uh, look for the function, it's variance, right? But here it says we have different ones for variance. So we have variance population and we have variance sample. Okay, but we will be always using the sample because we don't know the population variance, and that's impossible to do unless we're given a population variance. We will always be using the sample population. I mean sample variance because that's all we have, right? So let's just use sample variance. So var dot s, and then you just give it a range. So select these, close parentheses, enter, and let's see if we get the same answer. So there we go. We have the same answer. This is a variance using Excel function, and this is the one that we got. So I mean, it's always good to have the formula in mind because I mean most of the time we don't really use a formula, but because of the technology, it's so convenient if you just press the button, it gives everything for you. But I don't think there is any meaning to it if you don't understand what's going on, right? So I think it's a good practice for you to build these tables to work on the variance and manual practice. I think it's very helpful. So um, this is the class practice that we did together. And if you go to the next tab, and I'm gonna rename the first sheet, but here I put in the data, and this is a table for the length of long distance phone calls in minutes. Okay, so you have these data sets. So I've given you some questions. Construct a 5-number summary. Describe the average. What is the more significant average or median? And you have to find the variance. And I don't know why part E was there. So that's the class activity for you. So for finding the variance, I want you to do it 2 ways. I mean, using the Excel function is very easy and convenient, but I do want you to work on how to get the variance by formula. So just do the same as before, what we did before, like building xi minus x bar column and then squaring them, count if, and just finding the variance. Oh, I forgot one thing. So variance, and then we have to look. We have to find the standard deviation, right? We forgot to do that. Standard deviation, right? And we do that by taking the square root. And there is a square root function. This is how you use it as QRT. Root of a number, right? And then we're looking for square root of the variance. So enter, and this is the standard deviation. Or just using built-in Excel function, you can just do standard deviation. Standard deviation, right? So we have the same thing as STDEV dot P or S. But population, we're never going to use population, as I said before. So we're going to choose STDEV dot S. And then you just open parentheses and give it a range. Same thing. So A4 to A48. Close parentheses, enter. Oops, something was wrong. Okay, it wasn't A3 to A4. This is. Oops, sorry. I have to change the range to A4 down to A48, and then enter. See if we get the same answer. We do get the same answer. So this is the way of checking the answer for you. So find the variance, and then we can
also add find standard deviation. Okay, so these are five parts. I want you to work on it. I will give you about I don't know, 15 minutes to work on it. So please go ahead and work on this. And also, I forgot to tell you. So if you look at the tabs, here is the phone call tab, and we have another one called phone calls 2. Right? So this is the same, almost the same, almost. But it's different. I changed around one observation, so it might be different. So I want you to be aware of it. So please work on these two tabs. This is a class activity, and we will discuss it. Right? So I'll give you about 20 minutes to work on it. Right?